My name is Mateo Radic. As Professor Šerić told, I'm gonna hold up our presentation about scientific work evaluation of spatial interpolation methods for wind speed and direction, a case study in Split, Dalmatia County. So, starting with that, we are gonna go through the motivation and why do we need wind interpolation and accurate, precise data about wind speed and direction. Moving forward to study area and data we collected, the ways we did to determine scenarios and classification of events, interpolation methods, and then go through some tricks and approach we did to get results, and we are going to discuss about it. So the thing about wind, it's quite unpredictable, and areas when we can use it is a lot, starting from wildfire spreads, wind farms planning, and all of that. So moving forward to planning any kind of things that's require the wind, you have to have data about the wind. And the thing about wind is you don't have many measurement stations to get exact weather records. So we tried to do spatial interpolation to get data about the wind direction and speed across whole map. So the first challenge is you're coming to is you don't have enough dense accurate measurements about the wind because they're not so evenly divided across the map. Usually they are just put on some airports and some institutes. Then moving forward, we are looking about accuracy. How does accuracy goes along the whole year? As is it changing along the year, along the day, and along the types of winds blowing? So that pulls out the research question: how does interpolation accuracy vary across different conditions and methods? So looking here, we have our county. This is just Croatia neighborhood country, and this is like biggest county in Croatia. It's Split, Dalmatia County. And looking there, you have a lot of different climates starting from Mediterranean to continental, and you have a lot of areas starting from urban centers, coastal zones, and inland mountains. And looking here, you have only, like 10 years ago, you had only 10, not 10, like 6, 7 weather stations that could record and give you some weather records about the wind speed and wind measurement. So moving forward, now as we introduced and collect data from Weather Underground, and Weather Underground brings up to 52 weather stations that accurately give you all records about the wind. So that's a huge move forward, starting from 6, 7 weather stations only from airports and institutes. Now you have along the islands, along the coast, and even in countryside if you look up. And then we collected our weather records through whole year, 9 days randomly per every month, and that gets us around 1.5 million weather records. And most of the weather stations are configured; they're tracking every 5 minutes weather record. So starting for 52 stations that I showed in previous slide, we get the number of 28. How did we get there? So some of the weather stations are not so consistent. They're just getting installed a few months ago. Also, some of them were damaged or malfunctioning. So we had to have data consistency and complete data for the hold the whole year, through the whole year. And then we get clean and systemized data set ready for interpolation. So just as I said, first of all, we have 52 weather stations, and then we are grouping them by timestamps. And still, in some timestamps, we don't have measurements for like 15, 20 weather stations, and that's not enough. So we are discarding all the timestamps that have less than 30 timestamp, 30 weather stations per timestamp. Also, some of them are measuring not in same periodically. They're starting from 5 minutes, and some of them are measuring every 15, every 30 minutes, depending on configuration. And keeping in mind that's open source network, we had to group them and filter that like that. And then brings us to the data. Then bring us to the data from 1 million records per 1 year to around 100,000 records, better records. That's still more than enough to do some interpolation and measurements. After we cleaned and synced data, we did some scenarios. As I mentioned, it's important to have perspective, to have better accuracy during the summer or winter, so through the seasons of the year, and also keeping in mind what wind is blowing. And then we get 28 scenarios because you don't have so many maestral winds blowing through the winter. So that's the reason it's not just pure multiplication. And then we did some cross validations. We marked 24, so we have 28 weather stations, and we marked 24 as known. And the rest is 4 weather stations to determine how good is our interpolation. So we did 2 scenarios. One is typical equations, countryside, islands, canyons, and urban boulevards. And the second one is not so typical. It's just in a cluster of other more dense areas where we have other weather stations just around. So if you look here, this is our county. The first one is countryside, so you don't have any weather stations in range of 10 kilometers. And here's like also on a boulevard, in canyon, and on the island. And just here on different scenario, you have other weather stations densely populated around the ones. And we are moving forward with these 2 scenarios. Evaluation metrics we did was plain mean absolute error and root mean square error, just to determine how good are our interpolation methods. So interpolation methods we used was skimming with adjustment covariance. So in adjustment in the way we used for interpolating surface roughness, as it's not the same if you're having wind blowing or through the woods or through the urban area or over the lakes. And that's quite important for wildfire spread. Then we have ordinary kriging, inverse, inverse distance weighting, and classical natural neighbors. So when we did our interpolations with the data collected with 150,000 weather records, we determined the biggest errors and was produced by natural neighbors, while the kriging and ordinary kriging have the lowest error overall. Still, for all methods, maximum error was like 5 meters per second. In complex areas such as canyons, and keeping that in mind, we have a really strong Buddha wind just. Buddha is wind blowing from south, from north, and it's quite unpredictable. And moving forward and looking by performance by location. So you have to have in mind a lot of like surface roughness, slope, angle, all of that coming together, bringing us to canyon locations. So you have like river down, 2 mountains from the side, and it's quite unpredictable to determine accurately what speed and direction of the wind. So looking here, we have our weather station just placed in the Omish Canyon, where it was the biggest errors giving as they're placed within canyon. Even though you have accurate data just few kilometers from their measurement from actual weather station, it's still quite difficult to determine right wind speed and wind direction. And then We came to the conclusion that Bura wind have the highest interpolation errors across all methods, while Hugo and Maestral are more predictable, and we gain to lower errors up to 3.3 meters per second. And Bura, like I said, it's quite harder to predict as it's blowing in gusts. Looking here, we are seeing across all four methods, we are gaining huge errors, while for other things, like other winds such as Hugo and Maestral, we are getting nice results. So looking on zonal and meridional analyzed, so this before was like including all together, not separated, but by each component, zonal and meridian. While here, dividing by each method, you can expect Buddha is blowing from the north, so it's more expectable to gain bigger errors in zonal component, while meridional was smaller because it's not blowing east to west, it's blowing north to south. Here's our results for that, but still, it's not quite viewable because this is still for all winds, so for each station, but for all winds. So keeping that in mind, we have still wind blowing from north to east and east to west, north to south. But looking forward to detailed analysis for each wind, when looking on Maestral, we are gaining a much lower error, down to 2.2 meters per second, except the Trogir station. Trogir is the town placed just looking on the justs and hits of the Maestral winds. So that was expected to gain much better error results, and it was. It was going up to 5 meters per second, but looking forward, looking down there to other weather stations, quite good interpolations with low errors. Then we come into Bura, and as I said, Bura is the most unpredictable wind, and during the location of canyon, it was worse interpolations and with bigger errors. So there was a station placed in canyon that gave us biggest error, but still positioning of weather station is quite important. As before in Maestral wind that is blowing from west to east, still with Bura, it was placed inside the canyon, and canyon is positioned kind of looking in north. So that's the reason we are getting the most errors or interpolation across all methods. So we focused on the worst scenario. It's not there's no point on focused on best scenarios as a maestral to gain interpolation across whole map. Bura is unpredictable, so we focused on Bura win across whole map or across whole county. And looking at the resolution 100 meters, we determined wind speed and direction across whole map. Looking here you can clearly see four methods, and this one significantly different. The reason for that is because in here we are keeping in mind of surface roughness. So there's not just plain interpolation like other three methods. In here we have adjust covariance where we keeping place of height of the weather station above sea level, pressure, temperature, and most important surface roughness. So looking at this map, you can see circling around the places. Even though you don't have clear visual of the map topography, when you transfer it over it, you can see where the end of the islands are happening, and that's the places when the wind change speed and direction mostly. And looking on all together, rigging and ordinary rigging with adjusted covariance gave us the best result and captured terrain-driven patterns, and like I said, reflected geographical features. While natural neighbors, and the inverse distance grading was localized and not so good to predict on some larger scales, especially when we don't have some nearby stations. Then it's like most remote, as such as countryside weather stations that I show in the beginning. They are smoother, much smoother, but not so predictable, not so accurate. So order rigging gave us best overall accuracy for terrain complexity, canyons, and enclosed terrains. We had huge errors across all four methods, and Bura wind have the highest errors for all methods, while Yugo and Maestrals are lower and stable errors because they are not they are blowing more evenly. Coming to conclusion, we we collected data from all of our weather stations through the year, made interpolation for fall methods, determined we have better results and better interpolation for winds that are blowing more evenly and not so many gusts, and that it's kind of useful and predictable when you have, let's say, wildfire spread during Yugo wind that's typically blowing through the summer. It's easily to determine, even though you don't have accurate location, and the weather station can be as much as 5 kilometers remote from the place the wildfire spread started. In future work, we did some better classification of the winds, and starting from there, we are not just dividing winds as the time of the day or day of the month. We did classification that is we already did that. In our future work, we are thinking about including machine learning to get more better predictable, even though you have some times when just weather stations are not so available and you need your prediction right now. So we are bringing hybrid machine learning into it, and that's what we focus on our next work, and also broader range of wind types and scenarios, as I mentioned. So I did it with my professors from our university. We are coming from FES, we are from Split University in Croatia. So we are looking forward to hear more about any potential cooperations. And that would be it. Thank you for your attention, people.